on accident.
Okay, so last subunit in big unit A, which is most of the semester, we're going to do unit B towards the end, basically right after this, is about the periodic table. Question?
I lost my Chromebook in English, so I read it.
Quickly, get your Chromebook. Okay, so about the periodic table, the reason we call it the periodic table is because it's periodic. Does anybody know what periodic means? Okay, so in the library, there used to be a section called the periodicals, and it had magazines and newspapers. And you'd sit down in that section, you read a magazine and newspaper, and every week a new magazine came out.
Also, you can come out like at a certain time.
Exactly, in a pattern. So the reason the periodic table is called the periodic table is because the elements have patterns. And that's what we're going to learn today. So there's this thing called periodic law, which I'm going to restate in a little bit, that states that elements' properties are a function of their atomic number. It's pretty broad, but it would be better to say elements' properties are a function of the group they're in and their number of valence electrons. So that's the big one. Periodic law says that elements' properties are functions of their atomic number. It would be better to say periodic law states that elements' properties, chemical and physical properties, are functions of their group. In other words, elements in the same group have similar properties. And we're going to look at those groups today. Now, before we go any further, let's talk about what properties mean. There are two types of properties in chemistry. There's physical properties and chemical properties. This is something you learned in middle school. Does anyone remember the difference between physical and chemical? Okay. A physical property is something that can be reversed, like melting point. You can melt something and you can freeze something. So that's a physical property. A physical property is something that can be reversed, like melting point, boiling point. There's a couple others we're going to talk about. One called malleability, another called ductility. A physical property is something that can be reversed. A chemical property changes the identity of the substance. It's basically how elements bond with each other. Chemical properties are like flammability. It's really hard to get back a bunch of alcohol after you light it on fire because it makes new elements. You take the oxygen in, it makes carbon dioxide and water. So a chemical property is something that is a one-way property. You test it and it doesn't return the original substance. Okay. If that makes sense to you, first of all, give me a thumbs up. If any part of this is unclear, wave your hand around. All right, moving on. Cool. So this was like relevant like 10, 15 years ago. You guys don't really do like these kind of memes anymore, do you? But what do you notice if you are into this? What do you notice about the vertical columns? It's like troll face. What? So in a periodic table, whether it be the actual periodic table means there's a periodic table of superheroes. There's a periodic table of Pokemon. Yeah.
What's that Spider-Man one?
The pointing one? This is, I don't know. It's, the reason that these are down here is because the rare earths are just like all over the place. But what do you notice about the vertical columns?
They have like the same.
They're the same like structure.
Exactly. They're same general appearance, same general thing, but slightly different. With the periodic table of Pokemon, all the electric Pokemon are in one column. All the water Pokemon are in one column. All the fire Pokemon are in one column. All the ghosts are in one. Get the idea? And with superheroes, all the superheroes that can fly and shoot things from their eyes are in one column. All the superheroes made out of machines, like Cyborg and Iron Man, in one column. So in a periodic table, the columns are elements with similar properties. Is that cool?
Yeah.
Okay. So, tiny bit of history. I'm not allowed to teach you a lot of history. It's too bad because some of the history is just amazing. I would love to teach your European history, chemical history and European history together because there's a lot of really cool stuff. So, our study of the periodic table starts way back, hundreds of years ago. Well, 200 years ago-ish. There's this guy named Dmitry Mendeleev. Yeah, that's how you pronounce his name. Mendeleev. Because Britain, who knows why. Anyway, so they're like, oof, we need a letter combination for oof. EEV becomes oof. But anyway, Dmitry Mendeleev, he's in St. Petersburg. This was way before all the wars. This is end of the 19th century, or actually middle of the 19th century, beginning of the Industrial Revolution. And what he did is he took the 45 known elements and he grouped them according to their properties. First one to do that. There's a bunch of stuff. A bunch of guys had grouped them previously by various ways, but I'm not allowed to teach you about that. But he was the first one that grouped elements by their properties. And he noticed something interesting. When he grouped them by their properties, they went into this fun little grid. This is a replicate of his grid. And he noticed that there were holes. There's a hole. There's a hole. And based on where his holes were and the properties of the elements all around it, he said, you know what? That element right there, it should have these properties. It should have this density, it should have this malleability, it should be this flammable, whatever. And then he died. And then guess what happened? Did we discover the elements? Yes. Did they match his predictions? That's why we call him the father of modern chemistry, or the father of modern periodic table. Yeah, so they did. So we eventually discovered these elements, and they pretty well matched his predictions, which is great. But you might notice that this periodic table does not match our periodic table. Because as we discovered more and more elements, we were able to separate out the properties. And then this guy named John Newlands, another guy named Henry Moseley, they got together in Britain, and they said, you know what, we're going to arrange the elements by their atomic number. And when they did that, the properties kind of refined themselves. The elements that were like, kind of okay, separated out a little bit, till all the elements in the same column had similar properties. And this is the modern periodic table. It's arranged by atomic number so that the groups that we go down have similar properties. All right. Questions? If you're ready to move forward, give me a thumbs up. Moving forward. All right. So groups are elements with similar properties. I don't know why the groups is yellow. Anyway, so a group is a column of elements with similar properties. Some of the really famous groups, we're going to talk specifically about them, are the halogens. Each of these elements will do a number on you and me. Fluorine, chlorine, bromine. The reason we put chlorine in the pool is to kill bacteria in the pool. The reason we throw chlorine into the trenches in World War I is to suffocate people in World War I. They would get in their lungs and noble gases, they behave pretty much the same. If you put lithium in water, it's going to shh. If you put sodium in water, it's going to shh. If you put potassium in water, it's going to shh. They all react violently with water. So elements in the same group have similar properties, similar ending electron configurations, and similar valence electrons and oxidation. Basically, these last three things are exactly the same thing. If you remember your valence electrons, excellent. We're going to talk about it in about 90 seconds if you don't. So those are the groups. When we talk about groups, we're talking about vertical columns. One of our favorite groups is this group right here, copper, silver, gold. Those are, what should I call them for you? I'm going to call them the Warcraft metals. They're called the noble metals because it's what we use to make coins out of. Copper, silver, and gold. Some of the few metals you can actually find in the world as a block of that metal, in a vein of that thing. Almost all elements are found as compounds of things, but copper, silver, gold, veins. You're like, hey, it's a vein of silver. Just pop it out, I got a block of silver. Periods are the elements with similar highest energy levels. Period 1, energy level 1. Period 2, energy level 2. Period 3, energy level 3. Period 4, energy level 4. Period 5, energy level 5. Period 6, energy level 6. Period 7, energy level 7. And remember, the D block always gets pushed down once, and the F block gets pushed down twice. So all the elements in the highlighted period are in level 4. All their highest energy electrons are in level 4. Hydrogen and helium, only elements in period 1, and they're the only elements that have all their electrons in level 1. And then again, like I said, periodic law is properties are a regular function of their atomic number. I would recommend you learn that as properties are periodic functions of their group, because that's the most important thing. The test question is this: which element of these presented, so the multiple choice question, will have properties most similar to phosphorus? Yeah, probably nitrogen or arsenic, right? Elements right above or below it. Which property or which element is going to have chemical and physical properties most similar to calcium, magnesium, strontium? Get the idea? If you have questions, wave your hand around. If you're ready to move forward, give me a thumbs up. All right, moving forward. Octets. We talked about octets before. How many is an octet? 8. And it's 8 electrons from the S, right there, 1s2s, in the P. Actually, not 1s2s, S1, S2, P1, P2, P3, P4, P5, P6. So the octets happen when you have filled S and P orbitals. That is the goal, if atoms can have goals. That is the goal of every atom. Try to complete your outer shell with an octet. Look like a noble gas. Be isoelectronic with a noble gas. That's the goal. Be isoelectronic with a noble gas. And in the next unit, we're going to learn about how they do that by giving, taking, and sharing electrons. So again, both atoms and ions can have complete octets. Neon, 2s2, 2p6, has an octet. But the oxygen 2- ion is also 2s2, 2p6. So the oxygen 2- ion is isoelectronic with neon. Argon has an octet, 3s2, 3p6. The phosphorus 3- ion is isoelectronic with argon, because it also ends 3s2, 3p6. So neon, octet, stable. Argon, filled octet, stable. Oxygen, filled octet, stable ion. Phosphorus, filled octet, stable ion. And once again, the name we use for those electrons that get bought, sold, traded, and shared are valence electrons. It's the number of electrons in the highest S and P orbitals. All right, how we doing? If you're getting this, give me a thumbs up. If you're uncomfortable with any of this, wave your hand around. Moving on. We're good? We're good? Okay. Moving on. So we're going to talk about the broad chunks of the periodic table. Previously, we divided it into 4 pieces. We divided it into the S block, the P block, the D block, and the F block. And today we're going to divide it into about 7 more slices. So once again, elements in the same group have similar properties and similar ending electron configurations. Here's a word that we need to learn because we're going to use it a lot in the next, well, for the rest of the year. And the word is oxidation. It sounds like oxygen because it came around when there wasn't a lot of elements and they were mostly studying oxygen. But it's a fancy way of saying charge when something happens. And it's the number of protons minus the number of electrons, actually minus the number of, electrons, when something happens. Now, what that means is, we're going to talk quite a bit more about this later, just a hint. A neutral element with the same number of protons and electrons has an oxidation of what? That's a mathematical formula. Protons minus electrons is oxidation. So you have a neutral element with the same number of protons and electrons. What will its oxidation be? 0, exactly. If there's the same number of protons and electrons, the oxidation is just going to be 0. If an atom gains an electron, which is negatively charged, what will its oxidation be? -1. Okay. If it gains an electron, its oxidation is -1. If it gains 2, it's -2. If it loses a negative electron, what will its oxidation be? +1, exactly, +1. If it loses 2, +2. And so it goes. So elements on the periodic table go from -4 by gaining 4 electrons to +7 by losing 7 electrons. So that's their charge when something happens. Okay, so the basic groups, we're gonna look at each group in detail here in a second, so I'm gonna go through pretty fast. The first group we're gonna look at is the alkali metals. These are the alkali metals, group 1. Then we're gonna look at the alkaline earth metals, also in the S block of group 2. This whole D block is called the transition metals. The whole P block is called the main block, or sometimes main group. The group 17 is called the halogens. Group 18 is the noble gases. And then the entire F block are called the rare earth elements. Okay. If you have questions, wave your hand around. If you're ready to look at the properties of individual groups, give me a thumbs up. Okay, group 1. Group 1 metals are called alkali metals. They're in the S block. They end S1, and they have a +1 oxidation. Why do they have a +1 oxidation? Because they do what? Exactly, because they lost 1 electron, precisely. So, alkali metals have 1 valence electron, and they just yeet it away, and they have a +1 oxidation. Some properties of alkali metals: they're soft, they're highly reactive. I have some lithium in the back, I have some sodium in the back. Yeah?
Is that the same as like alkaline waters?
Unfortunately, no. Alkaline in water refers to its acidity or basicity. So the pH scale, which we don't get to talk about until AP Chem, unfortunately. Alkaline metals are those who are the opposite of acid, but basic. They are basic atoms. Fortunately, again, there's a lot of things in science. It's like, we're just going to borrow that word. But no, it's unfortunately no. When something is alkaline, it means it's basic. When something is basic, it means the opposite of acids. Okay. Yeah. They have a very weak hold on their electrons for reasons that we're going to talk about real soon, like tomorrow. We're going to talk about why properties exist the way they are. And alkali metals react violently with water. It's a lot of fun to put alkali metals in water. Again, we can do it with sodium. Lithium doesn't really do much, but we can do it with sodium. I leave my lithium sealed up. It's also a lot harder to get the sodium. I used to use potassium. I used to have potassium, but we can't have that anymore. Rubidium is really hard to get, and cesium is massively dangerous. And francium doesn't exist for very long, so you can't really buy it anyway. But if you're curious what happens when you put cesium in water, there's a link to a video on the Canvas video page. They are lustrous. Here's a fun word. What do you think lustrous means? Shiny, exactly, shiny. Yeah, luster, lustrous, shiny. Believe it or not, they're shiny. If I gave you a block of sodium, you'd be like, that doesn't look shiny. But then you cut it in half, and it would be shiny for a few seconds until it oxidizes. It's a fancy way of saying rust. Because they're so reactive, they react with the air and the water, and they become dull again. But if I take a piece of sodium and I rip it in half, it'll be like, hey, look, it's shiny. And then a few seconds later, it will become dull again. So that's what lustrous means. It's going to reflect light. They are electrically conductive, which we all know, because we all have lithium-ion batteries in our pockets most of the day. That's not a joke. They are lithium-ion batteries, meaning the lithium ion is what moves the electrons around, or what causes the electrons to move around. So when you say something's electrically conductive, it's able to pass a charge to the material, and it can form electrolytes. And we'll talk more about what electrolytes are in a future unit. But basically, an electrolyte is a solution that moves electrons. They have low melting points. I'll show you this later. And I guess now it's in January. Yeah, common reactions are in January. In January, I'll show you how easy it is to melt sodium. It's really easy. It doesn't take much at all. You could do it with a spoon on a flame. They have low densities. In fact, lithium is such a low density, it actually floats in mineral oil. The lithium metal floats in mineral oil. If you remember, a couple months ago, we did the Elements Property Lab, that little little glass ampule, and it had some lithium floating around in it in oil. When you turned it over, the oil went down, lithium went up. So lithium will actually float in mineral oil, which means it would also float in water if it didn't react. Okay, and then finally, ending configuration, something S1. 2S1 for lithium, 3S1 for sodium, 4S1 for potassium. All right, questions? If you're ready to move on to the next group, give me a thumbs up. Moving to the next group. Alkaline earth is group 2. Alkaline earth metals properties can be summed up in one sentence. Like the alkali metals, but not as much. Just like the alkali metals, just not as much. They're soft, but not as soft. They're reactive, but not as reactive. They're lustrous, but not as lustrous. They're electrically conductive, but not as electrically conductive. And they have higher melting points than group 1, and they're slightly more dense than group 1. They're not very dense, but they're slightly more dense than group 1. They don't have very high melting points, but slightly higher than group 1. They're still pretty soft, but harder than group 1. They're still pretty reactive, just not as much as group 1. That's group 2. Something S2. Questions? Usually when I say metals, the metal you're thinking about are the transition metals. So transition metals are the entire D block. Their oxidation varies from +1 to +7. 0 when they're alone, if they're a free element. We'll talk more about that later. Okay. If you're a free element, you have the same number of protons and electrons, so it's 0. But when they bond, they have an oxidation of +1 to +7. Some fun properties of transition metals. They are lustrous, you know this. So we make mirrors out of silver. Stainless steel is nice and shiny. And they're electrically conductive, of course. This is why we use copper for pretty much everything. It's really good for carrying electrons. Here's a fun word, Malleable. Malleable means able to be bent, shaped, or formed, and then hold that shape. The reason that your chair legs stay that way is they got heated up and bent into that shape and they stayed that way. That's malleability. Yeah.
What metal are chair legs made out of?
Steel, probably recycled cheap steel. Yeah, steel is iron with some iron with carbon and other things in it. Pure steel, like really good stuff, is iron with a very specific amount of carbon in it. Most likely your chair legs are recycled steel because nobody's relying on them to keep them alive. Car body will usually be virgin steel, meaning it's the first time it's ever been used. But yeah, they crush stuff up, they melt it down, they send it off to the people who make the chair legs, and the chair legs are recycled steel. Yeah.
What does malleable mean?
Able to be shaped and formed and hold that shape. Like somebody shaped all the pieces of metal of my step ladder, and it's still holding that shape. If I heat it up or bang it a few times, it will definitely not hold that shape anymore. It will hold the new shape. So you hammer a metal, it just stays that way. This is another one, another fun one. They're ductile. Ductile is a really neat property. It means it can be drawn into thin wires. Thank goodness. You can have copper wires just a few atoms thick. You got gold wires just a few atoms thick. And then, of course, the usual ones, they're hard. This is where you find the hardest elements on the planet, like iridium and tungsten and osmium. Well, iridium's the hardest. They're very dense, that's osmium, and they have very high melting points, that's tungsten. I don't know anything about rhenium, it's kind of interesting though. Highest melting point, most dense, hardest. Rhenium's right in the middle of that group. It's probably sharing properties of those other three. Other questions about the transition metals? Ready to move on to the main block? Give me a thumbs up. Question? Yes. Main block. P block. P block elements are the most varied elements on the periodic table. They're everywhere. They're everywhere and everything, all at once. So this is where we find solids, liquids, and gases. Elements at room temperature that are solids, liquids, and gases. We have, most of them are solids, but nitrogen, oxygen, fluorine, chlorine, those are gases at room temperature. And of course, all the noble gases. Bromine and bromine's a liquid at room temperature, which is wild. Gallium is almost a liquid at room temperature. This is where we find the metalloids. Metalloids are really cool. When we started using metalloids in the early 20th century, everything just blew up. Because we found that we could take this material and it was a non-metal, until we hit it with enough energy, then it acted like a metal. And that's what a metalloid does. It's an element that has properties of both metals and non-metals. We can make it behave like a metal or a non-metal as we need it to be. This is where we find elements like germanium, silicon, arsenic, antimony. These are metalloids. If we need them to act like a metal, we'll make them act like a metal. If we need them to act like a non-metal, we'll make them act like a non-metal. And that making elements do what we need them to do is how we made transistors. A transistor is a yes or no device. We basically say, hey, Gage, are you a metal? And you're like, no. And then Cohen pokes you, and you're like, I saw you, I'm a metal. So that's what a transistor is basically a gate where we send a signal and the gate opens. And when the signal goes away, the gate closes. And your phone has a little chip in it, about the size of your thumbnail, that has a couple billion of them. And those gates that are opening and closing make ones and zeros. And if you get enough ones and zeros together, you can make a computer program. That'll wait. And of course, this is also where we have the halogens, group 17. Halogens are cool. They're the next group we're going to talk about. Do you have any questions about the main block? Raise your hand. Question. If you want to talk about halogens, give me a thumbs up. Let's talk about the halogens. Halogens are all group 17. They all have a -1 charge, and they're in the p block. So they all end something p5. They're extremely reactive, and because they have 7 of 8 valence electrons, they want to get that 8th. So this gives them a very high electron affinity and a very high electronegativity. 2 terms that we're going to look at in detail next week. These are 2 of our trends. Electron affinity means it attracts electrons. Electronegativity means it takes them. Electron affinity means it attracts electrons. Electronegativity means it takes them, just like zoink or yoink. If you've got 7 and you only need 1 more to complete your octet, you're going to work really hard to get that last electron. Additionally, you're going to hold on to the 7 you've got. That's ionization energy. Ionization energy is the energy required to remove an electron from an atom. So if a halogen has 7, it's going to work real hard not to lose any of those 7. And because of that, they can attack most elements. Next week. Oh, no, tomorrow. Tomorrow you're watching a video about this very thing. It's called Holding Electrons. It's linked in Canvas. Pretty fun. It's like, hey, look at fluorine. Fluorine's jacking electrons. All right. If you have any questions about the halogens, wave your hand around. If you're ready to move on to the noble gases, give me a thumbs up. Move on to the noble gases. Noble gases are group 18. They have a oxidation of 0 because they don't want any electrons. They're perfectly happy with their completed octet. They have a naturally occurring completed octet, which gives them near 0 electron affinity, meaning they don't want any more electrons. They're happy with what they got. But they do have a very high ionization energy because they're happy with what they got and they don't want to lose any. So it takes a lot of energy to remove an electron from a noble gas. They make up a trace amount of our atmosphere. Just under 1% of our atmosphere is argon. A little bit of neon, a little bit of krypton, tiny bit of helium. Helium usually just leaves and goes up into space. A little bit of argon hanging around though. Where do you get noble gases? You get them from oceans. They get formed in the Earth's crust and then they bubble up through the oceans. And we just take a big old bowl and we just scoop them up. Just put them in a tank. And then this is going to be interesting because your generation is the first one where neon is pretty much nowhere anymore. It used to be everywhere. There's not a lot of neon anymore. Pretty much everything gets replaced with LEDs. In the process of removing all the neon, replacing with LEDs, because noble gases are really expensive now. So those giant neon signs that are filled with noble gases, it's worth it just to take the noble gases out and replace them with LEDs, because LEDs use a lot less energy. But anyway, so that's how they work. You run high energy through them, they form plasmas. I used to be able to point to the lights like, there's plasmas up there, but we just have LEDs now, which are better. We don't have any tubes of gas anymore. Nope, can't think of a single place that still has tubes of gas in here. But anyway, there we go. All right, if you have any questions about the noble gases, wave your hand around. If you're ready to move forward, give me a thumbs up. Last group we're going to talk about the rare earths. Big deal in the news. Why are rare earths so important? They make really powerful magnets. They have crazy magnetic properties, making them very, very excellent for making motors. If you know anything about motors, motors are just magnets that spin. So very heavy, very dense. Most of them are radioactive. The lanthanides are the first row. The actinides are the last row. Lanthanides end 4F something. The actinides end 5F something. Any element past uranium is called transuranium, literally beyond uranium. Uranium is the heaviest element that exists in our solar system as far as we know. All the rest have to be made somehow. Some are easy to make. They're really close to uranium, they're pretty easy to make. Some are crazy hard to make, like most of the end of the group or period 7 are really hard to make. They're really, really, really heavy ones. But everything past uranium, transuranium. They're artificial. I'm going to go forward and back. Yep, cool. Any questions? Okay. So you have the remainder 15, 20 minutes. Yeah, 15 minutes. Remainder 15 minutes to work on worksheet number 1. It has a matching skills test. I'm not going to be here tomorrow because my boy's getting his teeth drilled and I have a doctor's appointment too. So tomorrow you can also work on worksheet 1 and then watch the holding electrons video. You're going to love it. It's a cartoon. Question?
When you were the grades for the test,
They're not in already?
reminded me.
Oh, I will take a look at that. So real soon. Other questions? Okay. So use the remaining 15 minutes for worksheet 1 and the matching skills test, and then